Hello, everyone. So, Stephanie, do you know why I like computer vision? Because check this photo, and I passed it through some computer vision system which estimated my age, and it was pretty accurate. Give or take a decade or two. So, how not to fall in love with that? Safe Software is a company which is about 25. I think it's already 26 years around. We have tens of thousands of organizations that work with our software. We are represented in many countries, and we have very extensive partner network around the globe. But today I will begin with this story which happened to me before I began working with computer vision. I found it remarkable, so I even decided to make an Instagram story from it. And later I understood a little bit more about this mystery. So I take my pictures, and they all go with my phone, and they all go to Google Cloud, to Google Photos. And Google then reminds me every day, what happened to you like a year ago, 5 years ago, 10 years ago, and shows me photos. And if you know, Google Photos has a button. When you press it, it calls Google Lens. It tells you what is something about what is on the photo. So if it's a landmark, it can tell you some details, what it is, where it is, some history, or if it sees a plant or a dog, it can tell you what exactly that plant or that dog breed is. So last year, Google showed me this picture and said, in 2012, you went to Balboa Park and saw this building. Wonderful, I said, and pressed the button, Google Lens button, tell me more. And Google said, you know what? I see a text here, right there. And here is the text. You can see it below. I can show you here. Well, it didn't tell me much. It looked a little bit like maybe Georgian or Armenian alphabet, but certainly not one of those. So, well, I asked Google, tell me more. Well, apparently it was Telugu, a language native to India. So then, of course, Google not can only see something on pictures; it can also translate text. So I asked Google to translate it for me. So, and the translation goes as follow. So that text that we saw on the previous slide translates into English as, the gate is a battleground you'll never be able to reach. I found that was funny, and that could be, a good intro into a good story, or a sci-fi story, or maybe some mystery story. But today, certainly in the context of this webinar, it's more computer vision story. So how computers can see, and what do they see, and how it works. So I will try to explain how computer vision works for object detection, and then how we can use it within FME context, within geospatial context. So the end of this story, but the story of this webinar just begins. Computer vision, here is the definition that I took from Wikipedia. It's an interdisciplinary scientific field that deals with how computers can be made to gain high-level understanding from digital images or videos. And I have a problem with this definition because we are so far away from high-level understanding of anything. Well, not we, computers are. But I like more the second sentence, which says, from the perspective of engineering, it seeks to automate tasks that the human visual system can do. Of course, that's what we would like computers to do. Instead of us going and looking for certain things on images or videos, we would like computers to do that job for us. And here I copied the list of uses for computer vision from the same article. Medicine, yes, the holy grail is looking for brain tumors, and we are not there yet. Lots of papers, published every year, but still the work has to be done to do it reliably. Surveillance, space exploration, of course, those probes that go to Mars and even farther, they cannot rely on operators on Earth because the speed of light is, or radio signal is much slower than the time needed for a reaction on something on those planets. Autonomous vehicles, we hear a lot of stories these days about vehicles trying to drive around, doing very good things or crazy things. Military, manufacturing, for example, testing details that have some manufacturing defects. And the last item, I added it because it's relevant for us, it's geospatial. A lot of things that I know about computer vision and artificial intelligence, I take from this book, Rebooting AI, Building Artificial Intelligence We Can Trust. I attended a talk in March by Gary Marcus, one of the co-authors of this book, and that was really, really great, excellent talk. And I really recommend this book to everyone. It's not complicated. It's written really well written, really give you a really good idea of what artificial intelligence is, how it works, and why it's still not there where we should, where we expect, at least, as from a perspective of people who are not specialists, or what we expect artificial intelligence can do. For example, a couple of days ago, I received an email from my phone service provider. Would you like to upgrade your phone to a new shiny phone with a new camera, with artificial intelligence and deep learning? And I'm pretty sure the marketing department of Motorola has no idea what deep learning is. And from a common sense, like from a human point of view, deep learning means something like, comprehension, very deep understanding, but that's not what it is. So from my perspective, calling it wide learning is accurate as deep learning. Today, we will talk about a particular part of computer vision, object detection. Computer vision includes more things like identification. When computers identify a certain, very particular face, they know you, not just a human face. Figure or pose estimation, image restoration, object tracking. That's other applications of computer vision. And computers today do pretty good job with object detection. For example, here is an iconic bridge, and Amazon Recognition does a pretty good job seeing what it is and defining what it is. So you can see here, if I maybe zoom in a little bit, here you can see it's a bridge, and it certain with 97% that it is a bridge. Google Lens gives even more information about that. It tells that this is a Golden Gate Bridge, and gives you a few more links about that. And that's a global data set. So of course, they know everything about in the world. So this is a picture I took 2 years ago in Finland, in Porvoo, and of course, Google knows about that. But what is even more interesting, here is the picture of my mountain where I go every day with my dog. But I rarely see any humans there. But again, Google showed me exact same location, and it knows that it's Eagle Mountain. So, and that was pretty cool. On the other hand, sometimes, computer don't see how we see, or don't understand what they see. So in this case, Amazon Recognition thinks it's scarecrow. And it's not wrong, because if you have no idea about fire hydrants, hockey sticks, jerseys, maple leaf, then maybe you can think it's a scarecrow. But for us, we see it, and right away we build it into a context. So it's probably Canada. It's something about hockey. It's a fire hydrant on the back, and that's probably someone placing it in front of their house. You can see a road, house number on the left. So, or for example, this one. So we will talk a lot about fire hydrants today. If you see a pavement, you probably cannot conclude that this is an ice cream cone. Otherwise, you probably would see a crying kid somewhere in proximity, or maybe a happy dog licking it. Or this one. This is my son, but we don't want Google making a surveillance system implementing no dog policy. Because I don't like the consequences. Or here, for example, it's a picture in Edmonton from my hotel window. You can clearly see he's saying it Fifana, whatever that is. Well, I don't know. So again, it's mostly about gathering patterns, and I will explain how it works, than really understanding what's going on. So how it all works. First, what we do to teach computers see things, we collect lots and lots of samples. So here, as I said, I will talk a lot about fire hydrants. How it started, when I made my first project with stop signs, I mentioned it to a colleague, and he said, look, fire hydrants is a great, great object for detection, because one of the municipalities here in Lower Mainland has no idea where the fire hydrants are. So I started collecting them all around, well, not the world, but across North America for sure. So we collect the samples and annotate them, so basically show where the objects are. Then we train it. So, and there are many algorithms for seeing things. One of them is haar, and that is the algorithm that I used most for my tests. It works like that. So we take that small window showing the object, and then apply these haar-like features. So you can see these rectangles, and what they do, imagine your face, and you put a rectangle, for example, this one, on top of it. So the top one is over your forehead, and the black one below is over your eyes. If you calculate the sum of all the pixels in the top one and all the sum of pixels in the bottom one, and so you can get the idea that your forehead is usually brighter than the area of around your eyes. So that's how you can say that, well, when you see this pattern, it means that probably you look at a face. Of course, one is not enough, so it's just basically a random guess, just a little bit better than a random guess. But if you run millions and millions of those over your sample, then you get some patterns and collect some statistics. So, and computer vision is basically just collecting lots of patterns, statistics, and then applying that statistics to new images. So for this 48 by 48 pixel image, we get about 4 million those haar-like features, and they scan, slide through this sample, and make some conclusions about what is here. So, and then we just run this once we gather that statistic and created some knowledge, we run it through our images and make conclusions about what is on the picture. Not we, computers, of course. We can see it from us just looking at it and somehow knowing. So that's how it works. You can see it scans it, applying all those things, and I will scroll it to the middle. So, and then a computer can find something what matches the patterns and think that that might be a face, and it's not that sure, and it can try to find it a few times, and you can control that. So, for example, if you find a positive 10 times, then it's certainly a face. If it's less than 10 times, that it maybe not a face. So this is how it works. Then the image is rescaled, and this frame slides again, and it's rescaled again, and it slides again. I can go to the end. So, and we see that this face is found a few times, and actually you can do this yourself with a utility which comes with OpenCV, and it comes within FME as well. So you can create similar videos yourself. What computer vision tools are available these days? So quite a few. I will mention some. The big players: Amazon Recognition, Google Vision, Azure, of course, is there. OpenCV, that's where everything started for us. And Tensorflow. Tensorflow is not technically a computer vision system, but it's a library for analyzing and comparing graphs, and people use it quite successfully for computer vision purposes. So for those who are new to FME, it's our product where we build transformations, and I will be showing a few examples how we do that today. But basically, the idea is that we bring in any data, transform it in every possible way, save it to wherever the data needs to be, and then automate that. So you don't need to run the process manually every time. It can run based, by with a trigger or with an event or scheduled somehow. We will talk about building those workspaces today a little bit. So what is already available in FME? We have raster object detector family of transformers. They are based on OpenCV library. Recognition connector is already in FME 19.2 and coming soon, or maybe they already in FME, two more big players, Google Vision System and Azure, these two transformers. So they all, as you can see, we already have them on transformers. They're just going through the final stages of testing. I see 5 stages that make the object detection process. It's data collection, it's annotation, showing the objects on photos, it's training, then detection, the fun part, and once you detected your objects, it's reporting. I will go through the differences between using online services and making yourself, training yourself. So when you use Amazon or Google or Azure, of course you have their power behind. Lots of specialists, whereas when you do it yourself, you are the specialist, and if you are not, like I'm not a computer vision specialist, I'm an FME expert who played a lot with computer vision within FME. So that's the result will be as good as you are. They have unlimited computational power, where you may have just a single computer. They already know they annotated tens of thousands different objects, and their databases is huge, are huge, and they can run their tests every day. They have millions and millions of photos. Only from me, Google has over 10, well, probably over 100,000 photos, which I uploaded there for maybe last 15 years. And collecting and training is already done for you, whereas with your own data sets, you have to do it yourself. On the other hand, you decide what to detect. If there is something that those big players have no idea about, then you can do that. That's probably your only choice. And during my webinar, not webinar, workshop at GeoAlberta, I heard quite a few interesting scenarios. People would like to detect landmines, different patterns, different species of moss, because their spectral differences when you use multispectral images are not good enough, not distinctive enough to use those images for them. So, and I don't even have answers whether that's possible, but that would be interesting to try. And certainly those big players are not just, they won't do that out of the box as an out of the box solution. Of course, it requires online connection if you use them, and it might get costly. So I checked the prices and they look ridiculously cheap at the first glance, but it might get really costly very quickly if you, for example, process video or you have tens of thousands of pictures. And that I was really surprised to see how huge the environmental impact is when a model is trained. So I read that a well-trained model can have as big footprint, as big emission footprint as 5 cars throughout their life cycle, plus their manufacturing. So that's where probably, maybe not the cars will kill our planet, but maybe artificial intelligence and computer vision. So we will talk about data collection a little bit. I probably won't show the video, but it will be included into the slide, so you can watch it later. But often you can simply just place a camera on your dashboard and just drive around. So you can use existing data sets. Here I give a link to a stop sign collection. You can collect it yourself, go to outside and take pictures, or maybe go even inside. I made some inside projects as well. If you have aerial imagery, you can just digitize it, or you can generate samples, but I'm not going to talk about sample generator because it's the worst approach to generating data for your computer vision system. So you collect lots and lots of samples, collect even more negative samples. So you not only show objects, but you also have to collect data where you don't have your object, so that statistics knows where not to look for objects. And if it's a similar background, similar settings, then it makes a lot of sense, I think. So it looks like, it should, I think it should look like that. So, and then you can generate more negative sample by just simply clipping your objects from your positives, and I will show how you can do that. So let's now switch to a second stage, which is annotation. And here I will run my first demo. And this might be pretty boring, but I think it's a necessary process because a lot of people struggle with OpenCV library when they try to experiment with it, because it's very it requires to be very precise, the utility for annotating objects. So I will show it how it works, and you can refer to this video later so that you can repeat these steps. So you specify the path to your annotating utility, which comes with FME. I will write the path to it. This one, plugins, OpenCV. So this is the utility which helps you annotate photos. So I will run it like this so you can see it works. So, but if you have spaces in your path, for example, you install your programs into program files, place a quotation mark around, prefix it with ampersand space. So it still runs. If you use command prompt on Windows, then you don't need to do that. Then you type -A and type where your annotation file will go. So I will copy a path from here. We will save it to this folder. Copy. Paste here, and I will name it annotations txt. Then -I, it's the path to your images that you would like to annotate to show your objects. So I have here my positives. Again, I can simply copy this path. Copy. Paste. And it's important not to have a slash here. So OpenCV is a little bit, as I said, peevish maybe. It's not does not like any inconsistencies. So then -M is a parameter. So today our cameras make really big photos. So if your image is taller than 1000 pixels, you can scale it. And here I specify the scaling factor. So like that. I think I didn't make any mistakes. And if I press enter, I see my pictures. And then I just begin annotating my objects like that. I'm drawing a rectangle around, confirm it with C button, and then N brings me my next picture. So that's how I go through my photos.
We had a question if all the images need to be rectangular like this for this workflow.
Not necessarily. It doesn't matter. So you show your object, and I will mention what we can do about that. So here I simply annotated some, and most of those pictures were taken in January. And this is actually Regina in April. This is Albany again, Washington, DC, Lansing. So to me, it's now interesting collection. You probably, when you watch movies, you see just movies, and I see fire hydrants everywhere. And superhero movies, well, basically everywhere. Now I notice all the fire hydrants. This is Victoria, British Columbia. So lots and lots of places I visited. Sydney, British Columbia, Port Moody. I'm not telling you where this is, but I couldn't just resist. I already finished this project, but I started to take pictures of the fire hydrants everywhere. So that's how it's done.
It's the secret reason behind the FME World Tour, so that you get to travel the world.
Yes, I will visit a few more cities this year and next year, and I'm happy to take fire hydrants there. So, and this is the University of British Columbia. So that's it. So once you went through all your images, the utility stops, and you have a file. Here it is, and we can have a look inside. So this is how it looks like. It's the path to your image, then how many objects you have there, then the coordinates, pixel coordinates of the corner, and then the size of the window that you drew on that image. So, and that's probably, okay, let's go back to our slides.
Now, what if an image had multiple fire hydrants?
That's fine. You will just make a few rectangles around, and you will see, like, for example, in this line, let me turn on this pointer. So I have two, and then I have a double set of coordinates. So I already annotated a few. So now I will show you how you can turn your positives into negatives. Today I have lots of examples, and I'm not going to build any workspaces from scratch. So you saw this image, this file, where you have the file name. So that's our file names and the coordinates of the box on it. So what we want to do, using this file, create those boxes, those rectangles that we drew in annotation utility, and then using those rectangles as clippers for the images. So what I do here, I read it as a CSV file, I bring it in, and then I search for a certain pattern, which looks like this. Something what starts with P, then has, I can zoom in maybe, what starts with P, and then has 4 digits afterwards. That's the pattern of my image name. So that's how I will match my lines, those lines, with the images themselves. So then I rename attribute so that instead of columns 5, 6, 7, or 8, because this file has no column names, I will rename them to more convenient X, Y, D, X, and the Y. Then I build a rectangle so I can run this so that you can see the results. So here I can check my cached intermediate results. So I built all the boxes. And so those boxes will clip those the images, all the JPEG files, which I have here, all the positives that we just annotated, all those with Clipper. So, and I use grouping by FME base name. So that's the name of the JPEGs and the line that we extracted here, FME base name. So if I run this, it will clip my positives and turn them into negatives. Here how I assign the name. So I just say neg or negative from, and then the original name of the file of my positive. So that's what I will see. We don't need to generate a world file here, and really make sure that you don't compress your data, because computer vision systems really would like high quality images. What is good for human eyes is not that good for computer vision systems. So we probably can check whether something is going on already in our output folder. Yes, you can see. So now how we increased our negative collection by the number of our negatives, by the number of our positives. Let's go back to our slides.
Cool. We had some questions about point clouds, whether or not there's a way to label and run object detection models on point clouds.
So to use these tools that we have today, we would have to rasterize them. So if it's an aerial scan, then it should work quite easily. But for terrestrial or mobile scans, I'm not sure that it works really well. But we can think about that.
Maybe this user wants to try and get back to us.
Yeah, certainly. So of course that process of annotating photos wasn't that great, and certainly it's much better if you have more interactivity, when you can easier annotate and edit things. So that's what can be done with our traditional tools, like, well, any GIS. Here I used MapInfo for annotating cars and no car areas in a city. So, well, I didn't do that job. I found cheap labor, my kids. and they earned their $60 for annotating those cars, and they made 7,000 cars in 4 hours. So you can see that's pretty impressive. So that's what they did. So they went and just drew rectangles around them. Maybe while we are on this image, I should tell you that you can see that this city doesn't have all the angles, all the possible angles for the cars. So if you would like your collection to be more universal, you can use FME for example, maybe taking your samples and rotating them, and then just increasing the number of your positives and your negatives. I will show it in my next workspace that I have here, and I won't run it. I will just show you. You will get all those workspaces afterwards. So here is the workspace. I bring in my positives, which are green rectangles here. I just read them as a map info table, and my negatives, the red rectangles here, into my workflow, and the image itself, the photo. And what I do with positives, I extract their bounding boxes, their centers, and calculate. So what I do here, you can see that these rectangles have different proportions. Some of them are pretty close to square, some of them are quite elongated, some of them are oriented vertically, some of them horizontal. So I turn them all into squares, and here I have some logic in this workspace that turns all the rectangles into squares. So that's what I do here in this workspace, and in this transformer you can have a look. Then I build them just to see them, but I don't actually need this transformer. But I end up writing a text file which looks like this, because I have all the coordinates there, right? So I don't do annotation with the annotation utility. I do it with GIS package, whatever you like to use, and FME. And with negatives, here what I do, I will zoom in closer. I make a few copies and rotate them. Well, I make actually three copies and rotate them by 90, 180, and 270 degrees. And this way I multiply the number of my negatives by 4. So I have four times more negatives. So that's what I do without OpenCV utility, with just FME and MapInfo in this case. So annotation is done. And here I give you a few lessons learned. Sometimes, well, OpenCV is not always forgiving when you make a mistake. So I go through these problems that I found, and if you try to your own project, so here are some tips that you have to follow. So and then training begins, which is basically just setting up one transformer or two transformers and then waiting for quite some time. I will do it now. I will set one transformer.
Do all these demos work with older versions of FME?
They will work with the FME 2019 and later.
Perfect.
So raster object detector model trainer transformer. And this transformer and a few more, raster object detector, sample generator, and raster object detector model trainer, not trainer, sample preparer. Sample preparer. They come as FME package, and what they are is just basically they are wrappers around OpenCV code. They're Python wrappers around it. So that's why they might not work as well as full-fledged transformers coming with FME. I will tell what the problems might be with them. So what we have to do here, we'll prepare our samples. We say where our negatives are, and here is the first problem. So we select this folder. It does not like absolute path. So you have to change it to a relative path, like that. Our annotation file, the one that we just created, it is, well, either of them. And I will tell you about one problem again here. So I will remove this part. Come on. That number of sample 24, and the outputs again don't use absolute path. I will type background. Background is the same as your negative. These words used interchangeably in OpenCV. Output. So that this is the binary vector file which knows where your annotation are. So one more problem here. So OpenCV does not like this absolute path here. So here you have to use again your relative path. I will simply remove this portion like that, save it. Okay, so and if everything is good, this should run, unless I made a mistake. Yes, I made a mistake somewhere. Yeah, it doesn't find the images because data hydrants. Because this path should be relative to this to the annotation txt file, so I have to remove a little bit more like that. I'll do it again. So like that. Making mistakes is good because it teaches us where we might be wrong, but sometimes when it's really hard to go through the process, it's frustrating. So now it works. We generated the data for training, and now we can run the training. And training can run pretty quickly, maybe in 20 to 30 minutes if your data set is small, but then you cannot expect good results. I started a new training with my fire hydrants because, well, last time I did it was in May, and since that I collected 200 more fire hydrants. I started it last week and it still didn't finish. Yeah, speaking about the environmental impact. So here again, we pick our positive samples, our background file, so that VEC file that we just generated, webinar outputs, and again use a relative path here, background description, number of positive samples 24, number of negative, we had 22. Well, again, use as many as you possibly can find, and then you specify where you would like your intermediate files be saved and the detection model. That's the knowledge that you're looking for. It has some extra parameters, but they are chosen pretty carefully. Unless you know what you do, don't touch them. One more thing here. So sample width is 24 and sample height, that's the size of that window that slides across your images looking for patterns. So if you use it here, then you have to use the same values in the next transformer, which is if you use this size here in your positive samples setting in model preparer, then you also have to use them here in this transformer. So, and then you run it and you go for a coffee, for a lunch, or maybe for a vacation, and then once you're back, you have your file back. So your knowledge. I don't know how we keep information about objects in our brain, and actually this picture was made with FME. Talk to me if you like to know how. But computer knowledge can look like this. It's an XML file in this case, which contains lots and lots of statistics, and somehow by passing your image through this file, you get the objects back. So after that, the fun part comes. I will skip this video, you can watch it later. But now we will try to do some detection. I will go back to my workspace, to my workspaces. This one. And here I have a photo. I will show you, view the data. So, and I tried Amazon recognition on that, and Amazon is really great, but they probably didn't train a lot for oblique images or top-down images. So we will try to pass this data set through Amazon Recognition and through my OpenCV train algorithm. That was another project I tried, just basically walk around the office taking pictures out of the windows. So, and now I have a data set with about 400 cars for a few days, and we'll see how we perform here. So I won't run the recognition transformer here, but I will already save the results. And here I have my data set with my file cars from office. And I will run this and try to beat Amazon here. I will run the workspace now. So here we are. The image, Amazon found 5 cars and a person here. Can you see it? No?
There's a bird. Oh,
well, that's how it works. And that's me. And OpenCV, it's pretty good. I never trained this system to detect cars behind the street, so that's why you don't see too many positives around here. But that was my goal. I just really wanted to show the cars on the street. On the other hand, you can see how well computer vision works. It just does not have the knowledge, the statistics for smaller cars, or maybe placed at a little bit different angle. So if I would collect them, they probably also would be able to detect them, but I didn't do that, and that's the result.
We had some questions if people could use this workflow with satellite imagery.
I didn't try satellite imagery, but I tried aerial imagery, and that's my next. So I will show you a few results of my detection text. So here we see fire hydrants, and well, I mostly Port Moody, where I live, and collected most of my stop signs, fire hydrants, and you can see it worked quite well there. If you apply it to somewhere else under different conditions, your results might be not as good. Whereas for us, probably will be very easy to see fire hydrants of similar type everywhere. Of course, you can see some false positives here and here. Here is an aerial image, some parking lots and some industrial buildings. You can see it did pretty good job. So I trained it with about 400 or 500 cars, and sometimes it's puzzling why, for example, this car, I don't know. So for example, this car was detected and this car wasn't. But if you look not for precise amount of car, but maybe rather than statistics, how full your parking lot is, that's actually where this scenario came from. It's from University of Massachusetts, from our friends there who would like to manage better their parking lots. They would like to know, so probably maybe send a drone daily and estimate how well and how in general the patterns of the parking lot use work. So maybe for better management of the parking spaces. So you can see here a few false positives, for example, here and here. Often this algorithm finds things on the roofs looking like vents, look like vans for computer systems. Here's another one that we already tried. Of course, in geospatial world, we can easily extend our knowledge using geospatial information, such as building outlines or block boundaries. For example, if you're looking only for parking, then we can easily bring in our extra information, such as you can see here, the outlines of the buildings and the blocks, and use them as geospatial filters. And in this case, we can allow more false positives. It's a parameter that you can control, and since you can easily separate where you have your data, where your actual data is from whatever it is. It's not a car, you know that. So it works pretty well. Here I decreased a parameter of positives, or maybe when computer thinks it's a car, I decrease that number, allowing more false positives, because whatever is found, I just don't care, because I can easily exclude it from my final data set. So once you do that, finish your detection, you can begin reporting it somehow. I'm not going to talk a lot about that because it's not the purpose of this webinar, but I will show you a couple of examples how I deliver this results. So what you get from the transformers and Amazon Recognition and Google Vision work similarly. They output you. I probably will show you if I have time later how they work. They output rectangles around found objects. You can make a nice map with image rasterizer or Mapnik rasterizer. Make really fancy images. So I probably will make one. I will place Mapnik rasterizer here. We'll send my raster into this transformer. We'll send my recognition results to this transformer and my own results, and we'll style them. I will say this is a raster. This I will use a line with maybe I will make a thick green line around Amazon results, and I will turn my results. I will make them polygons. I will make them say orange, and I will turn them into circles, and I will make them semi-transparent. Then I will generate a raster, one, that's the spacing, and run this.
Have you run into a maximum number of objects that you can select?
Select or detect, you mean?
The question was select, but either.
Then I'm not sure.
Okay. Again, if they can try it out and let us know. There's a
limit. So here is the results. I made a nice picture out of it. So, but with Mapnik Rasterizer, you can do a lot of really, really cool things. We actually talked about Mapnik Rasterizer a couple of years ago, and I use it for not only for maps. I use it for everything. A couple of years ago, I made chocolate bars and wrappers for them actually with Mapnik Rasterizer. It's not the topic of the webinar, but you can see
I was lucky enough to get one. It was
yeah,
a good day.
I have a lot of fun at
it's
work.
One of your favorites, I think.
Then I made a couple of online services where you can test stop signs detection or fire hydrant detection. I can show you how it works. Again, so I took a picture of my son, but as I said, it's a professional deformation. I see everywhere stop signs and fire hydrants. So I will send this image to my online service. And here you can see a red frame around this sign. So that's my fire hydrant, my stop sign detectors object service, and I also have fire hydrant. I can run it on the same image, and you can imagine that if you have a few models, you can chain them and do detection in the same workspace. What's going on? Okay, there it is. I will send this image as well. And what is interesting about stop signs, so I also collected them around the world, and during the world tour last year, in every single city, I would take a picture of a stop sign, of a local stop sign, so that I always work with local data. And it worked really well everywhere, except Ottawa, where stop signs are in 2 languages. So in English and French. So they have a little bit different pattern then, and that prevents the algorithm from seeing them. What does it mean? It does not work? No, it means that you have to have all the samples that represent this stop sign. So if I had maybe like 50 stop signs from Ottawa for training, then it wouldn't be a problem. But what's also interesting, color is not taken into account. When I tried it on a Hawaiian stop sign, some of them are blue there. I just learned it last week. It still works. It's only brightness and the patterns within the window that looks for the object. So here we have our stops, our fire hydrants picture. So I was lucky enough to take a picture of 3 of my favorite subjects in a single shot. And then this is a good one, and you can have all the workspace with this one. So I showed you how I collected stop signs, basically driving around my neighborhood. And that was actually January, so you know how January in Lower Mainland of British Columbia looks like. So I just drove around, then I took that video, and I also collected a GPS track, and then I took the video, put it apart into frames, and matched the time of when each frame was taken with the GPS track, so I knew the location where each photo was taken. Then I passed those photos through my stop sign detection workspace, and I found the location of all the stop signs. So when I approach, of course, if I approach an intersection, I can get a few stop signs, for example, this one. How I selected the right one, well, they're all right, but the location is better. The closer to the stop sign, the better. So what I did, I basically measured their area of the detected stop sign, that rectangle that we received. And the bigger one, the biggest one, is the one that is closest to the actual location. So I can click that, and you can see what it is. So, and here is actually approaching my street. That's how my street looks like, you know, now. And as I said, this workspace is available, and the whole workflow and all the details about this. I did a blog article a while ago about this, maybe a year ago, and you can have that too. So it looks like we are pretty close to the end of our webinar, but I'm doing quite well time-wise. I probably will run one more workspace. So I will give you one more where you can show how you can make a mosaic from all the images into a single image and show all the objects are. So you can use this exercise 7, but I will show you how those transformers from Amazon and Google and Microsoft work with this example. So here I have this recognition connector. We can go inside. You have to have an account with Amazon, and you will use it for detecting your objects. So what you can do with that, so what you can send there, you can either send raster geometry, then bring in any raster and send it there, but make sure that you use proper interpretation. For example, RGB24 or whatever Amazon requires. Or you can just simply specify a path to your local file, or it can be a file on S3 storage. I will return back to raster geometry. That's what I send. And what we can do there, we can detect objects like we did today. We can find faces, image moderation. I didn't try that, but I think it's probably it is what we all think it is. And then text detection. So you, for example, can detect a stop sign, but it won't tell you that it's a stop sign. But then try to read it, detect the text. It will say it says stop. Then you can make a conclusion. It's a stop sign. So I will run it on the same, still on the same picture that we just tried. And here I have my raster object detector, which tries to detect hydrant model and then the stop sign, and with some standard settings in raster object detection, body, upper body. So I will run it. Here, from Amazon, we will get some output and some summary. And so the summary output port is also quite interesting. So we found 3 objects, as I expected, and Amazon found a few more. So here is the image. We found the stop sign, the fire hydrant, and the upper body of a person. Amazon found quite a few objects. I will change the color so that you see them better. That's fine. Okay. Here is the image. So let's check. So this is a person. This is a bench. Here is a road sign, a symbol, but we don't see that it's a stop sign. So you still can do that with the second recognition transformer. This is a fire hydrant, perfect. And this is, well, this is actually, you know, a city sculpture, a bear. We have them all around Vancouver, but well, it thinks it's a person. On the other hand, here it says it's a wheel of a machine, right? So, and that's quite good because it's covered with the bench. So, and here we have one more object, and it's again a person, which is strange. And this is not a person. So, okay, so you can see, right? So sometimes it does remarkably good job, but sometimes it's really strange because, as we said, it does not look, does not have deeper understanding what it is. It just looks for patterns and statistics and matching patterns and with the existing knowledge, with the existing numbers. So, and one more port that I wanted to mention is this one, the annotation. It doesn't have any graphic representation, but if I show it here, summary, it gives you a list of things that it sees here: a person, human, furniture, path, person is sitting, pedestrian, person, sidewalk, it's a path, pavement, clothing, lots of things that the transformer things are there. So with I tried it with Google Vision. I got results something like residential neighborhood. So that's right away I can think of analysis. You drive and you get some estimates what the transformer thinks is around it. So quite a few things here. So tree, plants, you see some plants there, and that's right, or some leaves you could see there. So you can match those maybe across multiple images and make some conclusions about scenery around yourself. So that's how it works. And that concludes our webinar. I give you a few links to some extra material. So this is the article where I talk about stop signs. A few links how detection works, what are those algorithms that I used. Here is that interesting article about environmental impact of AI. I just found it last week and decided to add it. And this is just a fun game. And then you can do something in front of your computer, doing something on camera, and somehow your machine will remember what you do and react accordingly. So if you have questions, we will stay for a few more minutes and answer them. But rather than that, thank you very much. And see you again at some other webinars.
Yes. No, I thought it was really awesome. We had a lot of really good questions coming in, so we will do a bit of overtime with Q&A. But for those who do have to leave, again, thank you so much for your time, and we hope this webinar inspired you. We will share out the workspaces and slides, and we really want you to take this material, run with it, and share your results with us. I know, Dimitri, you're really active on Twitter, so people can tweet their results to you, which is @Dimitri@Safe, or you can do @SafeSoftware, or post your questions in the FME community as well.
Yeah, try it, ask us questions if something does not work. I know for some people it was quite frustrating that it didn't work from the beginning, and I explained why it's that, so why we didn't fix those problems, because we just simply didn't do much for OpenCV software. We just made some wrappers around it. If you have some interesting ideas and materials, I certainly can help you with setting it up, and we can see whether it works. For us, as I mentioned, vegetation is what I'm really curious about, whether it can work with vegetation. So yeah, thank you.
We had a question about TensorFlow and whether or not it's available in FME.
No, yeah, that's I wanted to mention that, but no. So all those yes, it's not available in FME. How we do that, how we add something to FME, it's basically based on user demand. So if I just come to our developers and say, could you create me a TensorFlow transformer, they probably would say, well, no. But if users will request it, then certainly we'll consider adding it, so that in 10 years I could say, like, you know what, I asked for that 10 years ago. That's not a joke, that's what I always do.
So I would go and add that to the Knowledge Center where people can vote for it, and then you're more likely to get that in FME. We also had a question on whether or not this works with a video log. Could you take a video and run computer vision on something?
Yes, exactly. That's what I did with my stop signs. So if you go to slides and check the video, I didn't run the videos just because they don't broadcast that well. But if you look at the slides, you can see that. So I drove in my car around my neighborhood, and then I just took that video, split it into frames, and ran those frames. So so that's how it works, through splitting it into frames. And by the way, maybe, well, since the webinar is over, so I hope I'm not holding anyone. I drove in January, and it was about 3 o'clock, so the sun was pretty low, so the conditions weren't that good. So if I was driving towards the sun, then of course I couldn't see stop signs, and what can we say about poor computer vision? So it didn't work. So choose the proper lighting for your data sets, for collecting your data.
Mm-hmm. And then is there some dislocation meters between the frame stops and real life?
Yes, of course. So you won't be able to match it with surveyor precision, but it can be quite well, because we approach stop signs, at least we should, pretty slowly, so you can get quite a few frames pretty close to the intersection. So it will be a few meters, like maybe 5 to 10 meters. But of course, you also can place your camera differently, a little bit under different angle, maybe have a better camera, so you can play with those results. You also, I think, I didn't try that, but that's what I'm thinking towards, is to use the orientation that you can get with your camera, and maybe estimate the size of picture, so make some proportions. So if you know that the standard size of your sign, and you know that that many pixels correlate with that distance, then you can, knowing angle and the size, then you can estimate the distance to the location, and maybe get it with higher precision.
Mm-hmm. And then we had a question about the resolution of the imagery you were using.
Yeah. So, well, it's a broad question about resolution, but I will say so. I tried a few aerial images for cars, and it didn't work that well when the car size was about 30 to 40 pixels. So it worked not bad for detecting cars, but it was giving lots and lots of false positives. And certainly, enhancing, enriching your data set with geospatial tools probably will help you to get better detection results, like filtering whatever is not a road, so you don't get anything on the roof, or malls are terrible. Like, you get lots and lots of objects on mall roofs when you try those smaller ones, small resolution. Then I tried where you saw the parking lot example, those cars about 60 to 80 pixels, and it worked quite well. And it worked even better with the street photos, which I took from the office, and those cars are about 200 to 300 pixels. So it looks like it matters, yes. Then also resolution of your window that slides across your image when you train it also matters. So 24 by 24 is the default, and it worked quite well for stop signs, but didn't work that well for fire hydrants. For fire hydrants, I had to use 48 by 48 pixels, but it took much longer to train my data set.
Mm-hmm. So maybe just one or two more questions. This one, confirming that these tools only work with imagery and not with feature layers, say from contours of a DTM. Does that sound accurate?
This is accurate. Yes, yes, that's how you can get around it. So I see the question. The question ask whether making GeoTIFFs would be a workaround. Yes, that probably should work. Although I just wonder. Yeah, we can follow up with that one. It's an interesting one, but I'm not sure whether that's the best approach.
Okay. Well, I think that's probably all the questions. Will there be a GUI for detection learning for the user? Or is that what we call FME? I think that was to do with your first demo. It was an early question. Well, we may have missed that one.
I can see. Yeah, where do they go for detection learning? For the well, I don't think we will create more than we have today. So we have that utility that comes with FME plus, because FME is not an interactive tool, it doesn't interact directly with your data. You cannot go and touch it, right, with the mouse and edit it. We will leave it for GIS or CAD packages that you use.
Right. And then the last question that just came in, I know you addressed at the beginning of the webinar, of which institutions are interested in computer vision. And I know you referred to medicine, surveillance, space exploration, autonomous vehicles, military, manufacturing, and geospatial.
Since we mostly work with geospatial specialists, we hear most from them. So it's probably well, if we don't take our medicine, our project is BC Cancer Research, we probably 100% of other questions come from geospatial industry. Certainly there are much more applications, but how it all started, but it started like just a fun project for one of our developers. We have those innovation days when they do whatever they want. And one of our developers, Asher, he decided to try OpenCV, so that's how it. And he tried it on just normal objects which come with OpenCV, such as face detection, CAD detection, license plate detection. So those probably the areas where it works quite well. But for me, it always was a question of first of all geospatial. So that's my stop sign was the first one where I correlate images with geospatial, their location. And then during the world tour, in every single city where we went, I went to 7 cities, I was asked whether that is possible to use for geospatial, for the aerial imagery. And that's what I tried right afterwards with that car project. But I imagine it can be useful anywhere, but I just don't know. Matt, our old safer, is asking, any ideas about detecting other things like roads or other GIS features? So yes, so I mentioned a couple of examples, such as landmines and moss types and cracks on ice, for example. I heard a great scenario from our reseller in Malaysia, detecting roofs, not necessarily, the outlines of the building, just detecting their presence, because, for taxing purposes, they tax less buildings that they supply electricity to, and that was, something what they really wanted to understand what's going on. And another example, our reseller in Brazil, they tried it on garbage bins, and I think it worked quite well for them.
All right, I think we answered all the questions. I'm going to power it down, but thanks for everyone who stuck with us to the bitter end. If you have more questions, add Dimitri at SAFE or come to the FMUC and talk to him in person.
Yeah.
Thanks so much, everyone.
Thank you.